Welcome to the 5th webinar of the webinar series Coastal Resilience. The webinar series is organized by DCC-CR and its partners, CMCC and Deltares. This webinar is also the second webinar of the Co-Growth School, which is the first course of the DCC-CR Coastal Resilience School. Our partners, the DCC-CR Partner Alliance is made of, ourselves, DCC. I'm introducing myself, actually. My name is Cecilia, and I am the program manager of this DCC, Deltares, and CMCC. This slide allows you to join. We encourage you to subscribe to the newsletters and to visit our websites. If you don't have time to scan your codes, these codes now, you can write to us and we will give you all the indications. Okay, as I said, this is also the second webinar of the first course on called Sustainable Coastal Growth and Resilience. So we are expecting among the audience the 25 students of the course. Just a brief recap on the course, which is a comprehensive course targeting early career professionals, scientists and consultants, and people working on environmental agency. We are at the end of module 2, understanding coastal hazards using operational oceanography. The course is fully funded, and travel and accommodation will be covered by the DCC for the in-present week. Today's agenda sees the two speakers, Professor Ghada and Serafy from Deltares. She will start with a 30 minutes webinar. After that, we have a 10 minutes Q&A. And then we have a break, 20 minutes break. After the break, the second speaker, Professor Emanuela Clementi, will provide a presentation. Just a quick reminder that the Q&A session will be activated through the Q&A button in the Zoom. So you will have to write your questions in the Q&A session in Zoom. I also remember everybody that the webinar is recorded. Okay, so let me introduce you the first speaker. Ghada El-Serafy is a senior specialist in data sciences for ecosystem modeling and services. Ghada is an associate professor in data assimilation and optimization at Delft, the University of Delft, and plays a key role in strategic research at Deltares. Ghada is the coastal expert specialized in uncertainty and sensitivity analysis, data assimilation for environmental and ecosystem health, and integrated monitoring. She supervises PhD and master students and leads national and international projects. She's also a member of the Science Council of Deltares. So I now leave the floor to Ghada.
Thank you, Cecilia. So if you can share my presentation, that would be really nice.
Here we are.
Thank you. So today I will try to tackle one topic of interest, and I hope of interest to you, the sustainable marine and coastal information services. The content, next slide please, the content of this presentation is going to start with, next slide please. Yeah, thank you. It is going to give you some of the concept of services. What's the components, the main components in those services, how to set up a service for specific users or stakeholders. Then we are going to tackle the point of the co-design. Of course, plenty of people are talking about co-design. I'm going to try to explain a little bit the applicability of that, how to use it, and show some of the results that we have or the services that we use within Deltares, how to apply this information services for several sectors like ports or fisheries, wind farms, which is a very special sector. So, going through the content, I'm going to explain the needs, requirements, how to gather that, to provide maybe the information and recommendation for how to set up in your career and in your application services that are sustainable and what are their components. Next slide. So, having said that, I'm going to be looking at the coastal zone specifically. As you know, this is my expertise, and why the coastal zone and the information systems for the coastal zone is very challenging. Well, the coast, as you know, is having competing interests totally, and then also under a great deal of threat from climate change, from the different users, and the scale processes that really needs to have plenty of information with detailed information at different scales. So, having said that, we have, of course, the Earth observation part and the in situ measurements and the models that captures the scope of the coastal zone and how to provide this information provision in a sustainable manner, tailored to the specific user needs. This is the main topic of this webinar. Next, please. So I will go through these components or a flow chart that guides us in this tailored coastal information services. At the very top, you have, of course, the big providers of data, whether it's Copernicus Marine Services, Climate, and etc., or the ASA, which is the remote sensing component, and other data sets like in situ measurements from AMODNet or other type of database that contains data. And from the bottom part, you have the the demands of the users and the demands from the sector, and what type of questions are being asked from the users to be able to say which type of information that is needed to answer those questions. This is really at the bottom line. Of course, the top and the bottom should be the other way around. You start actually from the bottom, which is the question of the user. What do they need? And then you can go back to the top, which is the data that is available that would help you to answer those questions. Going through this flow chart, I would say, or workflow, after deciding on the questions that you have and the data that is available, you can choose from that what are you going to be doing. Is it only data processing from the satellite information and in situ, or merging them together? Then you can think about data fusion and artificial intelligence, data-driven models, or you need to forecast. So the question has having a component of forecasting and prediction. So then if you are talking about forecasting and prediction, then you can also use numerical models or hybrid models, including data assimilation, that you can really use for answering this prediction or the temporal component for the future. Once you have that, of course, there are several components that you still to think of, which is, do you need to store the data? Do you need to have an operational system? Or is it a descriptive prediction of understanding the system? If you have all of those answers actually gathered together, then you define your workflow, and from that, you have an information service. Next slide, please. This is just a setup of sustainable information services based on what I've just explained. Of course, there are components that are still missing, which is, are we going to be looking at uncertainties of our prediction? How are we going to validate this information services? Do we need to look at extreme events? Do we need to look at only visualization? So you really have to think of what is the output of this information service? And not from the scientific point of view or not from your own experience, but based on the user requirements. So this is very important that you keep in mind, that you have to think of who are the users, what do they want to see, how can I present my answers to the public. Next slide, please. As I said, for the operational modeling, which is part of this chain or workflow, we have to actually use plenty of components that is needed for us, like the operational modeling. And then you have the train of the models, because it's not only one model, and how to put them together. So, for example, if you would like to set up your operational modeling for a new area, then you really need to have boundary conditions. You need to have in situ measurement. As I said, remote sensing can be very useful, because then you can do a dynamic downscaling. Then you have your boundary condition for the modeling activities that you would like to have. It is very important in nowadays for information services that you have high resolution, specifically at the coastal zone, and then you can use the Copernicus Marine Services or others for downscaling purposes, and then you have your train of models or set of models in place. Next slide, please. User requirements. So then the services co-design. The co-design, of course, is an attractive word that is being used nowadays, but let me try to explain what a co-design means. So it is not only that you have the requirements from the user at the very first moment. It is very important for the user to be involved at every single step of the way in an iterative process. So you have your collection of requirements from the user, you go at the table, you do your design, you go back to the user and the stakeholders and show what you have. And that would be the first iteration with the users. Of course, not the users at large. You group the users in internal, the ones that are very close to the process. They do understand how it works, and then the external users that is of an outer circle. So you think of the stakeholders as circles along the way, and you have this iterative process. Every time you go, you collect your information, you show what you have designed, and then go back to actually the table again if needed, or you expand on your design. Finally, you develop the services with your knowledge of the sequence, but also with the knowledge of those experts, which are part of the user stakeholder engagement, or the external user, or the final users that would say, yes, I would like to have that in that way, only this indicator should be shown to me, etc., etc., etc. Next slide, please. As I said, this is a multiple events and workshop to collect the user feedback. So you can do that either through surveys or a direct interaction, or actually just a workshop or a webinar like this, and you can have their feedback into the process of your design. Next slide, please. So now I'm going to be showing some of the high resolution services based on the components that I just explained, including this co-design process. So I'm going to be showing actually that this service high resolution services that was for the aquaculture in Greece, in the Mediterranean Sea, that they would like to actually have a look at where to place and what are the threats for the cages that are placed in this area. So at that point in time and space, we have gone and done the co-design with the aquaculture sector. Um, uh, at that stage, at the very beginning, what do you want? Is it only cages for the fish? What type of fish is there? What are the threats that you are having? What answer would you like to do? They were interested in some of the temperature and the chlorophyll A. So we have designed a very simplified thing, though based on high resolution services. We have compiled this service provision was with Sentinel-2 data for the chlorophyll A and the optical sensing algorithm to retrieve that and provide them directly with that. We have also they wanted to have a very high resolution of 10 meter spatial resolution, and we looked at the combination of actually remote sensing with modeling activities to look at the prediction of the threats. What if the chlorophyll, if we detect the chlorophyll that is high from the satellite information, then we use some algorithm to predict what is it going to be higher than that, or is it going to decrease and issue a warning. Next slide, please. For the same thing, also for this project of High Sea, we were working with the port authorities, and we have been looking at actually the environmental impact of the navigation of the ships entering into the port and around the port. The ports, as you have seen, this is part of the green ports, which are very much dedicated to the ecosystem around them, and not to have harming effects of the navigation of the ships. So we have been looking at the most important parameter that they need, or variable that they need, which is the turbidity, as it was affecting actually the environment around it and the coasts around it. So they wanted to also have this turbidity, mapping of the turbidity. We used the same Sentinel-2 data, and we have been looking at the 10 meter spatial resolution, as this port was a very small port in Valencia. As you can see that this is, though we were using the same satellite information and most probably the same satellite information and resolution, we were providing two different services, one on turbidity and the other one on chlorophyll, for two different sectors according to their wish. Next slide, please. Machine learning and hybrid modeling, this is also one of the activities and the methodologies that is very much a trend. And it provides actually the best of two worlds. One which is the modeling, the numerical modeling, which is a very trusted model, and then the artificial intelligence. So that was for fisheries. And they have actually been looking at the Black Sea, which is a totally different behavior and a different system. And they wanted to have how can they provide information for the fisheries to be looking for where to fish, etc. I'm going to be showing some of them in more details, actually, in the couple of slides afterwards, and then to see the wide spectrum of services that is based actually on the same components as I've just mentioned. So this was based on the neural network. This is the methodology that we have been using. And we have combined the short-term chlorophyll A prediction and the nutrients, the dissolved oxygen, the sea surface temperature, all of those variables, we put them in the neural network to provide the information that is required for the fisheries. Next slide, please. Part of it was also the fronts. So they wanted to have the ocean fronts, the temperature, as I said, the temperature and the chlorophyll. We looked at the detection services contributing to a more efficient activity. So based on the front, that is being provided here, that the fishers can go and do the fishing activities according to the type of fish to those fronts. So in that sense, it is providing efficiency for the fishermen based on satellite information and model activities. Next slide, please. This is a very, let me put it that way, a very efficient way of modeling and using the models, very high resolution models, the ones that are very computational, with a high computational burden, but we use it in a very effective way. We call it on-demand services. We do not have to run the model for always or for a long period, but we only run the model when an incident happened. So it is an on-demand response service. So that would be, for example, if we know that there is a chlorophyll or a jellyfish, for example, or a bacterial bloom. So we start with the sources, knowing the sources of the spread, or knowing from certain citizen science sightings, then we say that this is the source, this has been observed from this place, what is the possibility or the probability that this is going to hit the shore or to arrive to that place at that time. And from there, it is some kind of a response to the sighting. We calculate according to that, to the particle track. We use the particle track models to actually see whether or not it's going to hit the shore, whether or not it's going to arrive to a place that it should not arrive to, and also calculate some of the responses that we have to do as a remediation that it hits the shore. Can be also for like the oil spill, but we are using it for jellyfish concentration and also habitats or other type of species that we do not, or bacterial infection. Next slide, please. That would be for suitability of fishing areas, also for the fisheries. When we provided them with the fronts, they were very happy with the service. They came back for more, and they came for this provision of decision support tool, where is the possibility to find fish or fishing suitability index, and we have provided them as an extension of the service that I have just said before. Next slide, please. Of course, the biodiversity and nature conservation, this is one of the most important activities nowadays due to biodiversity loss. And that is a very important part because you can use the remote sensing, you can use the model application as a potential application for biodiversity according to classifying habitats. Those activities is based on the bathymetry, and in the next slide, you can see that this is the bathymetry changes that we have been providing them for the depth, because for the biodiversity or the habitat, you need the depth information. And if you provide them with the depth information, they directly know what type of habitat suitability in the Wadden Sea. This is the Wadden Sea in the Netherlands. And then they can take conservation actions. Next slide, please. Talking about conservation and framework and strategy framework, one of the most important things for actually the policy type of user, that they do not need a full type of variable suit that they would like to work with. I mean, if they do not need a temperature and salinity and all of that, they need index or they need an indicator that support their strategy. And in that sense, most of the time we are doing a lot of data analysis and a lot of analysis trends and capture maps or statistics based on statistical analysis to provide them with a map of an indicator and around it some of the statistics of probability of increase or decrease. So this is one of the things that is also very much reflecting the type of user that you are dealing with dictates on you which type or part of this service chain that I've shown at the very beginning that you should adopt to capture their needs. Next slide, please. Now we are talking about a local user so far for fisheries at a certain zone or a port, one port, which is really local. However, the same concept applies if you are talking about global processes. So, for example, if you are talking about coastal erosion, then you can apply that for any part in the globe, and this is what I'm presenting here. So this is really something that we have been providing for a global coastal change processes, and this is the changes that we have. However, I have to make sure that you understand to provide a global service, that means that you have to have a huge validation set that it is applicable everywhere, and you have validated your results in several types of coastal activities or coastal line types. So this is very important to keep in mind. You still can apply the same concept, but you have to have a validation set to be able to say something about the accuracy of your system. Next slide, please. So this is just an illustration of this global coastal change portal that we can provide. Next slide. Effect of climate change, of course, because of those changes that I've just said. This is the coastal line assessment, specifically in the Netherlands, since we are below sea level waters, so we are already prone to a huge threat from the sea level rise. And we would like to test that, of course, by looking at the drivers to the coastal change, the forecasting of the shorelines that I just showed. However, to have this prediction into time, you have to have a very thorough understanding of the uncertainty associated with this prediction, because you are predicting not of a couple of days, you are predicting of years. Also, you are driven by scenarios that are having a wider uncertainty band. So when you are looking at the projections in time, you have to take into account this uncertainty. And of course, I can give you answers to the uncertainty analysis. This is a very important component when you are talking about projection into the future. So you really have to take that into account. Next slide, please. Okay. So as actually something that you really have to look when you are setting up an information services is how can you learn from the past to prevent the future. So part of the learning from the past is that you are setting up all of this information services actually in the past. You are collecting data from the past, you are looking at models in the past, you are calibrating the model on the past, and you are projecting the future. However, in this future, you have to look at data, you have to look at what is going to be available into the future, and you have to make this cycle in a moving window. And this is really what you have to look. It's not only now, and it's not only in the past. You have this moving window, and you are putting this window into the future as if it is going to happen. So this is I don't know if you can follow my talk now. So if you look at this thing, because I don't have actually the arrow, but it's okay. If you look at that, you look at the past, this line, which is the present, you are taking part of what you think is the present, but in the past. So for example, if you would like to set up this information service, you take 1 year in 2024, you collect all of the data till that point, you calibrate your model into that point, and then you say, okay, in 2024, that is my present, though we are now in 2025, and you say, okay, well, this is my present, assume I do not have data, let me see what my service would do, and then you play as if this is your future. You have the data and you check your results, you assess actually accordingly to the validation, and then you move this present line in 2024. In that way, you are moving actually this present or prediction window, and you can assess perfectly well whether your service is validated, yes or no, and what it is going to be doing. So this is really one of the things that you always do. Next slide. When you are working with assessment and planning. For some of the emerging, so now I have been talking about a single sector with single needs. Now, what if we have a multi-sectoral topic, like for example, multi-use? So for the multi-use at sea, this is a very important thing, because then you need to service not only one, but to service two sectors that might be having contradictory needs, and they can actually have to live with each other and have co-benefits from each other, and not a single one. Then you need to talk about the impact of one sector to the other sector, and you have to have an objective function, or you optimize their coexistence. Next slide, please. So to optimize actually this, we have developed an assessment and validation framework, which is really very much looking at several pillars: the technical pillar, the social economical pillar, the environmental one, the governance, the stakeholder engagement. And this is some kind of a framework that makes sure that you are looking at the two sectors or three sectors in a cohesive manner, and you are not benefiting one on top of the other, and you are looking at an optimization problem. Next slide, please. What we have also looked in this implementation and optimization of solutions, that we are not looking at one phase only. We are looking at pre-operational phase, we are looking at operational phase, and also post-operational phase, because there is decommissioning and impact on the environment. This is the only way that you can define this objective function or optimization technique. So you optimize in all possible phases that is included in the implementation of the solutions that you do provide. This is also a part, is not really co-design, but it is co-implementation, which is part of the most important part of the process. Next slide, please. Maybe this is just a look forward on the digital twin of the ocean. It is based on the same theory that I've looked at the very beginning. However, this is much more wider, much more interoperable, and having a lot of activities. So this is really a thing that we are doing now with the digital twin of the ocean, to look at different focus applications, to have a suite of models, and to have this plug and play, let me put it that way, plug and play part to perform certain sustainable information services. This is just an illustrative of the applications at hand, whether it's some biodiversity or zero carbon or zero pollution. We are also looking with respect to what if scenarios. The next slide, please. What if scenarios that deals also with the interference of policy strategies. And then you are looking at an illustration of this what if scenarios. You apply a scenario and then you look at the consequences, and yet again look at the impact, the positive and the negative impact on several sectors, and try to do the optimization. Next slide, please. So as a conclusion, again, the concept of sustainable information services is not that difficult. It is based on linking actually the existing platforms that provides information that you can use. You link what you know from the bottom, which is the user. Well, it should be on top, but it's okay. It is the user that drives your chain, and the design of your chain, service chain, that you put in place to answer one simple question or several questions, or you do an optimization technique. Only in that way you can provide sustainable marine information services. Thank you for your attention. Next slide. This is the thank you slide. Thank you. And if you please provide your questions in the Q&A, and if not, then I'm happy to actually give any answer through email. Thank you.
Thank you, Ghada, for the very useful information. I actually have a question before everybody else, which is, do you have any of paper on the project you have shown available for public to read for?
Yes, all of those examples that I've provided, they have been done in projects. I can provide the list. The projects are in EU projects, actually, European projects. So they do have sites, and all of that are listed on the sites. So I can do that. There is also a publication, an ongoing publication on this platform. So we have this HiC platform, and we are going to publish it soon. And I can definitely provide the link once it's published.
Okay, so then we can share it.
Of course.
With the audience. Thank you. I leave it to Edwin, who's going to read you the question from the Q&A.
Okay, thank you very much, Cecilia. Thank you, Professor Ghada, for your insightful presentation. First, we have a question from Susanta. She says, I'm Susanta from Sri Lanka. My question is, can we access high-resolution satellite images with spatial resolution of less than 10 meters, such as 3 meters or lower?
Yeah. Okay. Very nice question, actually, because as I said, the 10-meter resolution, this is really to be accessed through ESA platforms and through several Copernicus Marine Services and others. So in that sense, the 10 meter from the Sentinel-2, you can access that. Lower than this, then you have to contact ESA. If you are doing a research project or for educational purposes, I think you are granted access to a lower resolution. I'm not really sure if it is a commercial project, would you have the same access, yes or no? But I would advise you to contact either ESA, which is the European Space Agency, or look in the Copernicus Marine Services. Thank you.
Thank you very much. Then we have another question by Jewel Carter. You reference international data sets and the need for high-resolution data. How accurate is downscaling, and to what extent is supplemental local data required, especially in the context of SIDS?
So for the high resolution data, I think I answered the part on the satellite. So this is answered through the ESA. We do not provide that for the high resolution modeling. This is a numerical model that you do a high resolution of, and the downscaling is only for the boundaries, and it is pretty accurate depending on the accuracy of your model. So it is from large or coarse grid to lower coarse grid. It depends very much on the accuracy of the satellite information and also on the information that is being provided from your model. So I cannot say it's 10% accurate because it is this uncertainty that you associate according to the accuracy of the satellite information and the accuracy that you provide into your model or that you know about your model. This is propagated through the downscaling process or the subroutine that you do, and you get your answer through the propagation of those pieces of information. To what extent, I think this is the second part, to what extent is supplemental local data required? I think to a huge extent, because once you use this downscaling and you are providing an output, it would be really, of course, of a great help if you validate the output of this downscaling process or subroutine or algorithm with local data. So I'm never going to say that the local data is not required. The local data is required at all cases. The only thing is that you reduce the amount of local data required by using supplementary information from the satellite and from your model. Thank you.
Okay, thank you very much. Then we have Susanta, who asks, how small metapopulations with a scale of less than 8 meter or even 3 meter be effectively mapped using high-resolution images? Additionally, what is the accuracy of these images in relation to ground truth data?
This is a very technical question, and it depends on the population that you are talking about. For example, in the Wadden Sea, for example, it is the habitat that we are mapping, and according to the habitat that we know that they do exist, we make the correlation between the habitat and the population that is present in the Wadden Sea that we know it does. So it is some kind of, we are looking at habitat suitability, and from the habitat suitability, we are getting information on the population. So I cannot really answer your question because this depends on the population, where you are talking about, and what type of information do you have.
Okay, then we have Sharon, who asks, please, can you suggest simplified data analysis tools for coastal information system beginners can utilize or practice with?
That I can send you after this event or webinar. I can send you definitely through email. So because there are not one, but I can really give you the links directly through an email or something. Several of them. Would that answer the question?
Thank you very much. Then we have another question that says, you had 6 months weekly and real-time validation on one of your slides. Could you explain this some more?
Okay, I really cannot remember which one of the slides that I have 6 month and weekly and real-time validation. I think this is the one that deals with knowing the past to predict the future. The 6 month, I will try to explain as much as I know. I mean, from the slide, yeah, this one probably. You can send yes or no in a chat, then I know exactly if I'm talking about the same thing. Edwin, was a yes sent?
Not yet.
Okay, let me explain. In a general manner, so we have the 6 month validation, which is really very important. As I said, this is really the 6 month validation, weekly validation, and real time validation. It depends again on looking at the past to be able to predict the future. And I try to explain that this is a passing window or a moving window that you take with you. You have a set of data, so you gather information, for example, on 6 month validation, and you say, okay, well, I'm going to look at the first, for 1 year, and you say, okay, I'm going to look at the 6 month validation and play as if the other 6 month is into the future. And that is a 6 month validation. A weekly validation is when you have your system already set in place and you are revisiting actually your system if it is working properly on weekly basis, depending on the phenomena, of course, that you have. So for chlorophyll, for example, then weekly is fine. On a real-time validation, that depends, for example, if you are looking at the currents, or if you are looking at a daily event, or water level that rises or not. So it depends very much on what type of phenomena you are looking at. You have to be very careful in which time span that you are validating. And the validation is not only done once, it is done on a weekly basis or on a real-time validation. This is really if I'm predicting today, and then you validate what you are predicting on tomorrow. So this is the last thing.
Okay, thank you very much for your questions. Because of our time schedule, we won't be able to reply to all the questions, but we encourage you to post all the questions on the chat, and for the participants of our course, please submit your questions through our platform. Thank you very much.
Thank you.
Okay, so I'm going to share my screen again. So we are now at the end of the first speaker. So we have a break. It's a 20-minute break. We are going to reconvene at 10 past 3 in European time. So for the presentation of the second speaker, Emanuela Clementi's presentation. Thank you very much, and we'll keep being online until then. See you in a while. Bye-bye. Thank you, Ghada.
Thank you. Bye.
Had a chance to take a short break and recharge. Now we are ready to continue with the second part of our webinar. My name is, for those who don't know me, my name is Edwin Espina, and I'm a fellowship researcher at the DCC at the University of Bologna, and I'm very happy to host the second part of our webinar today. Some ground rules. Our second speaker will present her insights, and then we will follow with a Q&A section. Please feel free to submit your questions in the Q&A section, and we will address as many as possible. And finally, please note that this webinar is being recorded, and it will be made available for educational and promotional purposes. By participating, you consent to this recording. Now, it is my pleasure to introduce you to our next speaker, Emanuela Clementi. Emanuela is an environmental engineer with a PhD in hydraulic and maritime engineering. She has over a decade of experience in operational numerical forecasting, and she specializes in the Mediterranean sea dynamics and wave current interactions. Currently, she leads the Copernicus Mediterranean Monitoring and Forecasting Center, overseeing the development of a coupled wave current modeling system. We are honored to have her today to share her expertise, and please remember to submit your questions in the Q&A section, as we will address them at the end of her presentation. Now, without any further ado, Emanuela, the floor is yours.
Thank you, Edwin. So I'm going to share my screen. Okay. So good afternoon, everyone. Yeah, I'm Emanuela Clementi. I work at the CMCC, and today I will try to give you an overview on my experience in regional ocean forecasting systems. I will start with a short introduction on sort of an historical overview of the ocean prediction, and then I will go through the main pillars of ocean forecasting, which are the ocean observing systems, the numerical models, so how we usually set up ocean models for forecasting purposes. And then I will go a little bit more into details into the Copernicus Marine Service, and especially for the Mediterranean forecasting system. And finally, I will conclude with some example of application and extreme events that are then, let's say, provided through the Mediterranean forecasting system. So starting from a brief, let's say, historical introduction, we know that until the first decades of the 19th century, oceanography was mainly governed by a naturalistic approach. So we were exploring unknown regions and collecting basic scientific observations. After that, it was in 1822 and 48 when Navier-Stokes determined the dynamic equations that nobody attempted to solve until the beginning of the 20th century, that explains the time evolution of the ocean state variables. And then we have later in 1942 the first publication of the first work that was connecting the theory and experimental data in a synthetic work called The Oceans. Since then, predictions have been defined and are defined as the result of solving the time evolution of systems when both the initial conditions and boundary conditions in a three-dimensional environment are known. And this process is also known as integration. The first attempt to forecast a variable was done to forecast wind waves. In 1947, Sverdrup and Mank described the theory and the practical methodology to forecast surface wind waves, thanks to the strong connection to wind forecasting. Later, sea level was the second variable, ocean variables that was forecasting, and this was practically done thanks to the link with astronomical tidal forcing, winds, and atmospheric pressure. It was only in 1983 that the first successful forecast of an entire 3D ocean currents was carried out. It was published in the work of Robinson and colleagues in 1984. It was the first experiment when 2-week ocean weather prediction was produced for the California ocean current system. So since then, three main pillars have been defined to be the core of the ocean prediction science. On one side, we have observations, which are multidisciplinary, multi-platform, can be permanent or relocatable in the ocean. We have numerical models for hydrodynamics, ecosystems that can be coupled or forced with the atmospheric data, and data assimilation, which is the way we ingest observations into numerical models and are providing optimal field estimates and uncertainty estimates. So, other than that, operational oceanography is even more important because it is the way we can provide scientifically based information to the users, forecasts of the state of the ocean in a routine basis with a sufficient speed that has to be useful for the users to take decisions in time and before the relevant conditions of the sea are changed. So I will go now through a brief description of the ocean observing systems, which is, so we have a broad range of ocean observational data types, and we can subdivide in two main methods, the remote sensing and the in situ observational instruments. For the remote sensing, this is based on satellite data that are a major asset for oceanographic research and are mainly based on high precision altimeters. These instruments measure the sea surface deformation, slopes and currents. Infrared radiometers that measure sea surface temperature. Visible radiometers that measure ocean color, so the chlorophyll. Scatterometers for the wind speed and direction. SAR that measure surface currents. The added value of these instruments is that they are providing observations since a long time period. So we have a continuous series of observations available from these instruments. They can cover the world or global ocean, and they usually provide with a high space and time resolution. In addition to that, we have also in situ sampling. Through in situ measurements, we can have information and the main variables for the water column, such as temperature, salinity, currents, but also sea level, and biogeochemical data, for example, that are measured through tide gauges, in situ vertical profilers, gliders, moorings, drifters, ships, and other instruments. Of course, the quality, quantity, and availability of the observational data have a direct impact into the quality of the ocean analysis and forecast, and as a consequence also to the associated services, as before Ghada was presenting several of them. Just an overview of a couple of remote sensing instruments that are usually used for ocean forecasting. The first one are the altimeters. Altimeters are the active radar that can measure the sea level, the sea surface displacement. They measure the distance between the satellite and the sea surface and the position of the satellite with respect to a reference ellipsoid. They usually have a high precision of few centimeters for long distances. And we are collecting this type of observations since the beginning of the 1990s. So we have several decades of observations that have been preserved thanks to the launch of several missions. And thanks to that, for example, we have the possibility to monitor the sea level trend since the beginning of the 1990s. This is a picture from the NOAA website. And as you can see here, it's clearly depicted a continuous increase in time of the sea level, which is mainly due to the added water from melting ice sheets and glaciers and to the expansion of seawater due to the fact that the ocean water is also warming in time. The other satellite measurements that we usually use in forecasting systems are sea surface temperature measurements. In this case, the instrument receives the radiation which is emitted from the surface of the sea. We measure this variable through two different sensors, thermal infrared and passive microwave. Thermal infrared measurements are, let's say, have a long heritage since they are measuring the sea surface since several decades and have also a high resolution. But those are impacted by the presence of clouds. So under clouds, we don't have the possibility to measure the sea surface temperature through this type of instruments. On the other side, passive microwaves can measure also below the clouds, but can be affected by wind-generated draftiness and by precipitations. With respect to the thermal infrared, in this case, passive microwave usually have lower accuracy and the resolution is even lower than with respect to the thermal infrared measurements. Moving to the in situ data, in situ measurements have been collected since the beginning of the 20th century, but mainly thanks to bottles. And since the 1950, as you can see, in the ocean, we had only few observations. Starting from this date, several other instruments were launched and were used to measure the water column content. And after 2004, thanks to the launch of Argo vertical profilers, and gliders as well, it was possible to largely increase the number of observations that we can have in the ocean. And now, this is on the right, a picture from the situation in January this year. This is how now the actual in situ observing systems are distributed along in the world ocean, and especially you can notice how several regions are still undersampled, while there is a larger coverage of measurements in other regions of the ocean. I will move now to the second component that I was mentioning at the beginning, which are the numerical ocean models, which are the core of our forecasting systems. So usually for ocean hydrodynamic models, we use to integrate the primitive equations. We usually use Boussinesq hydrostatic and incompressible approximations. Those are usually the way numerical ocean models at mesoscale resolution are standardized for ocean forecasting. All these 7 equations in 7 unknowns that you see here are the basis of our numerical models. Integration in time and space are the core of our numerical models, and all these equations are, as you can see, strictly interrelated, but there is a strong relationship with the atmosphere. So we need to specify carefully the atmospheric boundary conditions, since there is a continuous exchange of mass, temperature and momentum with the atmosphere. So this is one of the critical part in setting up an ocean forecasting model. The other critical part is related to the discretization, the spatial discretization, to define which is the best way to discretize our model, our domain. We can use regular grid, which is a series of equally spaced lines, or irregular grids, which instead is composed by a series of usually triangular grids that can vary in size. Usually we have lower resolution in open sea and higher resolution in coastal areas or in areas where we need to have an increased resolution. Vertical discretization is also fundamental to be defined when we implement a forecasting system. First of all, because the ocean surface is time dependent, and because the ocean floor is also depending on the geographical positions from 0 to several kilometers. So there are several, for example, vertical discretization that can be chosen: Z coordinate, S, sigma, hybrid, and non-linear free surface, for example. Another critical aspect when you have to implement an ocean forecasting system is to define the initial condition for your model. These initial conditions are the starting values of the variables that you want to predict. Here I listed several examples. Climatologies can be initial condition from your system. This consists of an average in time for a long period, usually at least seasons or better for years, mean of the essential ocean variables. Usually temperature and salinity, climatological data are used to initialize our system, but in this case, we need to define a spin-up period, a period in which velocity fields needs to balance with the density field. Observational data can also use as initial condition. This is usually an approach that is taken for a relocatable system mostly, because it's quite difficult to use observations directly since they are irregularly spaced, and it is difficult to define a gridded data set for initialize a model run. The other possibility is to initialize our model thanks to a previous model run, usually from a coarser grid model. In this case, you need to perform interpolation in space. For regional forecasting systems, as the one that I'm going to show you in a few slides, an important condition are the lateral boundary conditions, an important a key aspect. We can have closed boundary conditions. We can decide not to have water flowing across the boundary. In this case, free slip or no slip condition can be chosen according to the needs of your system. Open boundaries instead allows the waves and all the disturbances that originates within the model domain to leave it without affecting the interior solution. And in this case, several methods can be applied, such as nesting, specific boundary conditions specified, so the values are specified directly at the boundary, or radiative or sponge boundaries, for example. Another possibility is to define periodic or cyclic boundary condition. In this case, we usually use this type of boundary condition for channel flows. So we have seen that we have in situ observations can measure the water column, but are sparse in space. They cover only a part of the ocean. And satellite observations, which on the other side can measure a larger domain, but are limited to the surface. Then when we build our forecasting system, we make use of numerical models that can provide the time evolution of the three-dimensional properties of the ocean. So they can cover the entire ocean domain, but of course at a defined resolution. Observations can be assimilated into our model to correct the initial conditions for the forecast. So when we have correction to the initial condition, we have analysis fields that are the best initial condition for our model predictions. Then when we provide this information through a routine approach and fully supported production and delivery of the data, we perform operational numerical modeling systems. And one of the major operational services that we have that we can access is the Copernicus Marine Service. The Copernicus Marine Service is funded by the European Commission. It's implemented by Mercator Ocean International, and any user can access, after registration, the data that are delivered through this service, which are free and regular and systematic information of the state of the blue ocean, physics, meaning currents, temperature, salinity, and waves, white ocean, sea ice, and green ocean, the biochemistry for the global ocean and for regional seas. The data that are provided through the Copernicus Marine Service are observations in situ and space data and numerical data, so the ones that I'm going to illustrate in a while. This is the way you can access the Copernicus products through the Copernicus Marine Catalog. There are several sections that you can access. The first one, which is the most relevant, is the Ocean Products Catalog. Ocean Products Catalog provide observational products for the past, which are multi-year, reprocessed, and delayed time data, and near real-time data, which are instead close to present day. For the numerical products, you can again access past data, multi-year, reanalysis. Reanalysis are consistent reconstruction of the ocean thanks to numerical model with assimilation of observations. These are usually provided starting from 1993, so starting from the altimeter satellite era, or even before. Near real-time data instead consists of analysis and forecast. The analysis usually cover the previous 2 years. Instead, the forecast data are provided for the next 10 days. But you can also access the Ocean State Report, which is a yearly publication that is providing a contribution to the assessment of the state of the ocean for the regional seas and the global ocean. Ocean monitoring indicators are a series of indicators that are produced and constantly extended in time, and they are, let's say, a way to monitor the ocean variability. They are based on multi-year reanalysis and reprocessed data, observational data. And finally, you can also access and visualize the products through the ocean visualization tools that are provided again into the website. So I'm going now to concentrate more on the numerical products, which are provided by the monitoring and forecasting centers. 7 monitoring and forecasting centers have been established within the Copernicus Marine Service, 1 for the global ocean and 6 regional seas. And I will concentrate on the Mediterranean Sea. The Mediterranean Forecasting Center is a consortium of 4 institutes, and CMCC is leading this consortium and is also responsible for the production of the physical component, which is the one into the middle, and OGS in Trieste and HCMR in Greece are instead responsible for the production of the biochemical and the wave products respectively. All these 2 systems are forced by the physical data that are produced by CMCC. Those modeling systems are all based on state-of-the-art community models. They are all assimilated in situ and satellite observations and are forced by high-resolution atmospheric data. We usually improve yearly our systems, so there is a continuous improvement of the systems that is meant to provide a better accuracy of the products that we release. All the developments are fully consistent among the 3 systems in order to be jointly upgraded. So I'm now going to give more details on the physical component, which is built by a 2-way coupled system, ocean general circulation model based on NEMO, which also include tides, and the wave model, which in this case is WaveWatch 3. These 2 systems are implemented at 4 kilometers resolution and are 2-way hourly coupled. The coupling consists in providing surface currents and earthly temperature difference from NEMO to WaveWatch, and on the other side, WaveWatch. So the wave model provides to NEMO the neutral surface drag coefficient, which is used to compute the wind stress. The forcing fields that we use to force our system are high resolution ECMWF, European Center for Medium Weather Forecast data at 1/10 of resolution and at the highest temporal resolution available. We have implemented also 39 freshwater river inputs that are retrieved through another Copernicus service and through the EFAS, which is the European Flood Warning System datasets, and consists of daily mean river runoff of these 39 major rivers identified. And of course, we have open boundary conditions. The major one is the one that connects the Mediterranean Sea into the Atlantic. And here we are nested into the Copernicus Global Ocean, which has 112 degrees resolution and 50 vertical levels. But we have also another open boundary conditions, which is smaller here on the eastern part of the domain, which is the Dardanelles Strait. That is the strait that connects the Mediterranean Sea to the Black Sea through the Marmara Sea. In this case, the forcing fields are daily climatologies that have been extracted from a box model of the Turkish tree system. We assimilate data, as already anticipated. We use a three-dimensional variational scheme, which is called Ocean Bar. We assimilate sea level anomaly from altimetry with all available satellite tracks and vertical profiles of temperature and salinity, mostly from Argo, gliders, and XBT. And in this picture, you can see how many observations we assimilate in 1 week. We also use sea surface temperature data from satellite, but not for a direct assimilation, but for correcting the non-solar heat fluxes in NEMO. As we have implemented an operational system, this is a sketch that represents the operational chain. So we every day produce 10 days forecast. So 10 days forecast are forced by atmospheric forecasting data from ECMWF. Each day we initialize our forecast through a simulation that is forced with analysis atmospheric data. And once a week, this simulation is reinitialized through a 2 weeks analysis run. So during these 2 weeks, we assimilate all the available observations that provides the best initial condition, and usually this is done on Tuesday. A big effort is done in order to validate our model, so to provide a description of the quality of the data that we release. We perform this operationally, meaning that every week we provide an extension of the validation of the previous week analysis. And in this case, you see a time series of the root mean square difference for the sea level anomaly. So a comparison of the model output with respect to all the available satellites, which has a mean of 2.7 centimeter, which is quite low error since it is close to the error of the instruments. All this validation is published on our website, which is medfs.cmcc.it, where we also publish the validation of the temperature in depth. Here you see a Moeller plot of depth versus time of the root mean square error for temperature, which is model temperature, which is compared with Argo, gliders, and XBTs. As you can clearly notice, the largest error are concentrated at a depth between 20 to 60 meters, and in the seasons at the end of summer and in autumn period, when we have in this area where the thermocline is placed. And this is quite common for forecasting systems to correctly predict the strong variation in depth of the temperature, the strong gradient in temperature that is formed during the stratified season. As you can see from this plot here, for example, this is a transect in the northern Adriatic Sea that shows how the temperature is well mixed during the winter period and instead is strongly stratified during the autumn period. And this huge gradient of temperature in depth is critical to be simulated by models. So that's why you see here these larger errors. Similarly, for salinity, you can notice a larger error in the surface and subsurface with, again, these seasonal variability of the error with larger values in autumn period. Again, this is published on our medfs.cmcc website. Another validation that we perform is published on the Copernicus Marine website and the product quality dashboard. It provides not only the validation of the analysis, but also validation of the forecasts. In this picture, for example, you can see for temperature, the temperature values from the observations in green and from the model in blue. The dashed area here represent the number of observations. In the middle panel, you see the bias and the error. The bias is depicted here in green and the error in blue. You see that we have the analysis error and bias, which are usually lower with respect to the forecast error, which is usually slightly larger with respect to the analysis. And also the correlation coefficient, which again shows how the model correlates with the observations. I'm showing here a similar plot for the model salinity. In this case is between 0 to 10 meters. Again, you can see how the model fits with the observations. And this again is published on the Copernicus Marine website. I would like now to move to applications. So how we can use our data in order to analyze specific events and extreme events in particular. And this is one of the applications that I wanted to show you. It is related to the Medicane-Llanos. So Medicanes are Mediterranean tropical-like cyclones. This one is was a huge Medicane, the strongest storms recorded since 1969. And it was impacting the Ionian Sea in Greece between 14 and 20 of September 2020 with very high wind speed up to 110 kilometers per hour, huge rain and flooding that caused damages and also deaths. So investigating such type of events through observations, you can notice that it is very difficult due to the sparse availability and the low availability of observations. While with the modeling data, you can analyze these events through three-dimensional discretization and the revolution in time. So this is the how the Medicane-Llanos developed. So it started in the northern coast of Africa and then moved northward and eastward, reached the coast of Greece, and then decreased in intensity the days after towards southeast. And this is how our model was able to simulate this type of event. Here you see in black line the path of the Medicane, and the model was able to represent the sea level increase that you can see on the left part then the increase in the surface currents and the increase on the significant wave height. So this tree shows how the model was able to not only mimic the path of the Medicaid, but also the timing, which is highlighted by these squares that shows when the minimum of the atmospheric pressure was reached along this path. We then validated the results of this for this event. First of all, we evaluated the sea level, since we had the possibility to compare the sea level from the model to a tide gauge, which is located in the coastal areas of Greek here, Ghada column. And this is a time series from the model in blue and from observation in black. And at the peak of the event, so when the storm reached the coast, we had an underestimation of about 4 centimeters from the model sea level. Then we wanted to also check how our model was able to provide reliable boundary conditions to a high resolution model, which was implemented here in this red box domain. It was based on a Scheiffen model and a structured grid model. And here you see in red, the line, the curve that was representing the sea level simulated by the high resolution model, which was able to eliminate the underestimation of the larger grid model. We also validated the significant wave height, in this case using satellite data. Here in this plot, you see 3 different tracks of 3 different satellites in 3 different times during the passage of the Medicaid in the area. The colored area represents the model, and the circles here instead represent the values of the satellite. And in the bottom plot, you can clearly see how the model, which is in black, fits very well with the observations. So very high correlation between model and observation during the event. And thanks to the sea surface temperature satellite observation, we were able also to measure the decrease in temperature in the area where the Medicaid passed. So this in the top is the model temperature difference between the final and the initial time of the Medicaid and the satellite on the bottom. So the general pattern between the two is quite similar, and the decrease of about 3.5 degrees was captured by the model. Of course, it's clear that the satellite was not able to correctly provide information along the path of the Medicaid due to the presence of clouds. This is why this area is quite smoothed. Another extreme event, which was forecasted by our Mediterranean forecasting systems, is represented by marine heat waves. This is a work that was published by a colleague, Ronan McAdam, in 2024. You see an example here for 2 different areas in the Mediterranean Sea, Ligurian Sea and Gulf of Taranto. The red line represents here the sea surface temperature climatology. The dashed red line is this extreme, so is the maximum threshold for marine heat waves, 90th percentile of sea surface temperature. The gray line instead represents the sea surface temperature measured, and the blue instead represents the Mediterranean forecasting data that you can see. It's quite well representing the evolution of the sea surface temperature and the definition of the marine heat waves, which are this area represented by these orange areas. We also use our Mediterranean forecasting system to provide forecast for extreme events of storm surge, or as in this case for Venice Acqua Alta, which is extreme events occurring in the northern Adriatic Sea. In this case, it was a prediction that we did for November 22 Aqualt event. So we were around 19 of November when we forecasted a sea level increase up to 161 centimeter. That was then recorded by observation to be 162. So only 1 centimeter underestimation of this extreme event. So I'm going now to conclude here. So just to remind that the forecasts are critical for a wide range of applications that includes marine safety, fisheries management, pollution control, climate studies, for example, and are also important for decision making and offshore operational and coastal infrastructure protections. And with this, I thank you all for your attention, and I'm available for questions.
Thank you very much, Emanuela, for this insightful presentation. And now we open the floor for questions. If you have any questions, please post it on the Q&A function. And I would like to start the question section to ask you that since many professionals and participants of our course are working out sectors related somehow in some way to coastal resilience, and would be also interested in implementing a platform with services similar to the ones that we saw on your presentation for generation, download, and data visualization. What would be the key requirements, technologies, and best practices to consider when developing such a platform? I mean, where should we start in terms of infrastructure, data sources, and user accessibility? Thank you very much.
Sure. Yes, this is a relevant question. So first of all, the Copernicus Marine Service is the first, let's say, point of access where anyone can, let's say, access data, observational data and modeling data. So once you have all these data, you can start building your higher resolution, for example, numerical system for design for coastal areas. Then, as I mentioned in my presentation, there are several setup of the model that have to be implemented, and this is actually a choice that the modeler should take. So depending on the region and the processes mostly that you want to simulate. There are actually, yes, best practices, always refinement, but and there is also the attempt with the digital twin of the ocean to provide to new users, for example, a way to implement ocean forecasting systems where they can already retrieve the data tools that can be used to implement as at the first stage a forecasting system.
Thank you, Emanuela. Maybe while we read the Q&A question, I have another question for you. In the last slide, you listed several sectors or stakeholders that would benefit from the modeling you provide. I did not see, or maybe I misread, the insurance sector and insurance companies. I wonder if I would imagine that your model could be used by the insurance sector that need to decide if providing insurance for a specific area based on the level of risk. So I'm wondering if you have started some sort of conversation with that sector, or if it's not up to you. I mean, who else at CMCC does that? Thank you.
Thank you for the question. Yes, actually not directly, but of course the product that we release are useful for this kind of sector. Maybe not directly forecast, but for sure the reanalysis and the reprocessed data, so the long time series that represent the state of the ocean in the past decades. This is a way to define area that are most subject to risks, for example, flooding and so on. And yeah, for sure, thanks to this data, the user and insurance, for example, in the insurance sector, they can retrieve useful information to define which are the areas and which are the limits of, for example, sea level or temperature, whatever. Thanks to this long time series of reconstruction of the state of the ocean. Then the forecast will be also useful in order to, let's say, protect and mitigate the extreme events.
Thank you.
Thank you very much. Then we have Taina, who asks, in case of lack of observational in situ data, how can we compensate the range of error in the numerical models projections?
Yeah, usually you can, you can start with, if you don't have near real-time data, for example, you can go through past observations and retrieve climatologies and try to bias correct your solution. Or you can make use of other projections that are released in order to compare. But usually, and you can then for sure work on your parameterization, the setup of your model. But yeah, if you don't have a reference, then it's quite complicated to define the level of accuracy of your projection. Yeah.
Okay, thank you very much. Then we have Isa, who asks, how can these imageries be processed? Kindly provide necessary links.
Processed, okay, so I showed some images that are already provided through the website that I mentioned in my presentation. Usually, so the one that we provided through our MedFS CMCC website are made through Python scripts. Those are operational tools that every week perform a validation of the model with respect to available observations. Instead, the one that I provided in the for the Copernicus from the Copernicus Marine Dashboard, you can directly retrieve from the website. You can play with the variables, the data set you want to use for validation. So it's quite easy. There are the links in my presentation in case it's useful. I can provide directly the links. Yeah, it's mostly that.
Yes, thank you. Then maybe we can let the audience know that, as we said earlier, you can write to us, to the DCC address, and difa.dcc-cr@unibo.it, and we can provide you the information, the links, we can help you find the links that you're looking for the last question and so forth.
Okay, thank you, Cecilia, and thank you all for your insightful questions, and a big thank you to Emanuela for such an engaging presentation. Now I am delighted to announce our next webinar speaker. We will be joined on March 4 by Mary Pendle from HR Wallingford, who will share her expertise on topics also related to coastal resilience. And this will be another fantastic opportunity to learn from leading experts and engage in meaningful discussions. With this, we end our webinar for today, and stay tuned for more details, and don't forget to mark your calendars. Have a nice day. Bye-bye.
Goodbye.